and welcome. In this video, we're going to look at a quick parallel circuit overview. We know that in parallel, two or more resistors can be connected to the same point, and that is said to be in parallel. And it kind of looks like this here, where we have this node here, where these two resistors are connected to that same exact node. And then at the end here, we see that they can even connect back together to the same node as well. And we can calculate that total resistance in parallel using our total resistance equation here. It says that RT is equal to 1 over 1 divided by R1 plus 1 divided by R2. And so if we know what R1 and R2 are, we can plug that into this equation here. And this equation actually identifies our Ohm's law and KVL and KCL. KCL says that the total current is going to be the sum of the branch currents. And we know that in parallel, if we were to follow our current through here, we see current enters the node and divides out. Some current goes towards the first resistor, some current goes towards the second resistor, and at the end they hit the second node here and they come back together. So we expect IT at the beginning and IT at the end, and we can say I1 down the first branch and I2 down the second branch. And depending on what those values of the resistors are, is going to determine the current flow down that branch. So if those two resistors are equal, then they're going to divide equally their current. But if one of those resistors is smaller than the other, then the smaller resistor is going to have more current than the larger resistor. And that's what this total resistance equation is identifying. It's saying that we have a known voltage. Our voltage is going to stay the same. The total voltage is equal to the voltage down each branch. And so we can use that up here. We can say that this 1 right here actually represents a voltage. And this 1 over here actually represents a voltage. Anytime we have a 1 in here, we're going to say that that's a voltage. And if we look, we see that that's voltage over resistance. Ohm's law says that that's current. So we know that we have a voltage on top here, voltage, divided by a current for the first resistor plus a current for the second resistor. And we know that the added up currents is going to be our total current, IT. If we sum our current branches up, we get our total, which means that now we have voltage over current. And voltage over current is equal to resistance. And that's why we can get our total resistance out of this equation, because it works off of all of our expectations. We can also predict the current paths down each branch. That's using our current divider equation. The current divider equation says the want current, so that could be I1, divided by is equal to the total resistance, that's the resistance that we have in the circuit, divided by the resistance that we want to know the current through, multiplied by the total current. So down here we have that applied. We say that we have looking for the I1 current, the current down that first branch. We're going to use the R1, which is the resistance in that branch, and put the total resistance on top using our total resistance equation, and then multiply that by the total current. And that's going to give us that current division down that singular branch. Note that this is upside down from the voltage divider equation. Right before it was want over half, now it's half over want for our current, and that's because our current and our resistance are inversely proportional. So power in parallel works a lot like power in series. We'll see that there is an easier power equation to use for this one. We can say that the power is equal to voltage squared over resistance. And since we know that the voltage stays the same in our parallel circuits down each branch, we can use our voltage source as that squared voltage and then use the value of our resistor. And that makes it a little bit easier because now you don't need to find the current down each branch. Right? So if we were looking for power through the R1 resistor, we would need the voltage, and that could be the voltage source because the voltage stays the same. We'd have to multiply by the current down that resistor, I1. Right? But in this one, we can say that this is just the voltage source and the R1 resistor, and that's going to give us the R1 power. So that makes it a little bit easier on us. You can use the other ones. If you find the current down the branch, you know the resistance of the branch, and you don't know the voltage source, you can use some of these other power equations. But this one here that uses the voltage squared over resistance is going to give you the most direct version of this for parallel. Okay, let us know if you have any questions.